Hello everyone, a very good afternoon and welcome to this workshop. So as Mayank has already said, this workshop is divided into three parts and I will be taking the part one. So this is based on the feedback where most of the audience they wanted to know about various use cases that we are doing, but also there was a good amount of audience who wanted to get an overview of the AI. Henceforth, I'll be taking with the part one, which is Introduction to AI. So let's get started. So the topics which I'll be covering mainly is that I won't be going in depth of any of the topic, but just I will touch upon the surface of what it is and also, explain out various terminologies that you may hear about. So these are the outlines. We'll talk about some current AI trends. Then we'll talk about the definitions of AI, ML, and DL and how they are related to each other. Then we'll talk about why deep learning is so hyped, and then we'll see a difference between ML and DL. And then we'll see different kinds of learning like supervised, semi-supervised, unsupervised, and reinforcement. And then we'll see what is regression classification. Then we'll touch upon what is transfer learning. And then finally, we'll see how the AI pipeline works. So, but first of all, this is a very popular meme that you would have seen in the internet. So this is what, society thinks or what your friends thinks or what other things. But at the end of the day, in deep learning or in AI general, what you do is simply programming. This is what we do. And this is also a very nice definition by Michael Nielsen. Also, he has used this definition for neural networks, but I think we can generalize it for AI. So these are nothing but a programming paradigm. So if you are doing programming, this AI or doing programming with ML, it's similar to that, but a different paradigm of programming. That's all it is. And it enables the computer to learn from the data that it sees. And just to give an example, so this is an AI algorithm which recognizes an elephant. This is really a complex task, and this can be done with just this, 10 to 12 lines of code. That's all it is. So you can also do that, just a different way of programming as you can see on the screen. So before I get started, so these are two pictures. So this one of them is generated by AI, and one is the original picture. So can anyone guess which one is original and which one is uh, generated by the AI? Well, if you see, the left one is the real image and the right one is generated image. But you can see, how progressive AI has been and how advanced it is now that it can generate up to, 10 power 6 pixel resolution clarity of image, and this looks very real. And there are some other AI algorithms like this one, which was released last month by OpenAI. Here you'll just give sentence prompt, and based on the sentence, the AI algorithm has developed this understanding or learning that it can generate the entire paragraph based on this sentence. And this is another movie called Sunspring. It's on YouTube, and its script was written by another AI algorithm. And this is another AI algorithm, hide and seek agent by OpenAI. So here, this is a simulated environment, and this agent they have to hide from the intruders. And initially, they have this block, so they automatically by themselves figure out that they need to close this door in order to hide or avoid the intruders, and they succeed in that. And they'll do it by themselves. They learn it themselves. And this was the same kind of algorithm which created kind of news all over the world in 2016 when one of the AI algorithm called AlphaGo from DeepMind it defeated the champion Lee Sedol in the game of Go. Now this game of Go is really complex. It has more number of moves than there are number of atoms in the known universe. So you can imagine the complexity of the game. And these are some other examples from again Google DeepMind. This was released this month where they using AI algorithm they are able to improve the estimated time arrival of different transports by on average of 50% in different location. And this is another example of AI algorithm where they're able to even predict the protein structure. And this all started long back, but it's helping in the COVID research. So blue one is the predicted structure and green one is the original structure. And this is another good example where the engineers they use these ML algorithm to control the different parameters of the data center, and they're able to reduce the amount of energy required to cool the data center by 40%. So that's a good amount of reduction. And these are some myriads of application that you'd be using in daily life, starting from Amazon Alexa, Google Home, or Netflix, or your shopping, your Facebook, your mails, or even in the medical diagnosis. They're kind of used everywhere. And this is another series by produced by Robert Downey Jr. and even hosted by him, where they explain, what goodness the AI is bringing in different domains of our life. So you can watch this. It's really good. It's the age of AI. So with that motivation, let's get started. So, AI was always there. So why all of this sudden we have this hype of AI? So this was because of one technology called deep learning that has created all this, fuzz and all these new startups, and this has become the what do you say? People may think it's a panacea for all the solution, and that's because of this technology called deep learning. And this all started around in 2012. When the deep learning algorithm was used called convolution neural network, which defeated other algorithms, and after that, it's all has been the deep learning. And even from this graph you can see that around 2013, the exponential rise in the use of deep learning in various services and applications by Google. Now, why this deep learning is so successful, or why it has created so much hype? So I have just consolidated it in these four reasons. So one is obviously deep learning comes with better and faster learning techniques. And then we now have huge amount of data, really huge amount of data. For example, on Facebook, there are 1 billion images uploaded per day, or on YouTube, there are 300 hours of video being uploaded every minute. And this good amount of data, leads to better learning. And there was this release of very good libraries by individuals and all the giant tech companies like Google, Facebook. And this library really enables you to code out all these AI algorithms very easily, and prototype very quickly, and experiment very quickly without worrying about this complex mathematics and linear algebra behind this. And the fourth one is obviously accessible to high compute GPUs. So this GPU coming to each one of us, or to every practitioner at a good rate, made it accessible to explore different algorithms, and they were even customized to support the deep learning algorithms. So now we just saw why the hype of AI is in this era right now. This entire decade has been the decade because of the deep learning. But just to start with, how does AI, ML, and deep learning falls with respect to each other? So first is artificial intelligence. This is the one which we want to achieve, and it refers to computers or any machine with the ability to reason and mimic cognitions as human. And then machine learning is a subset of AI. Now machine learning is a type of is a technique to achieve AI. And in this, what happens is computers will have the ability to learn themselves given the task without being explicitly programmed for that task. So you do not define any rules, or you do not write any rules, just give them the task, and they themselves will learn and do it. And then deep learning is a subset of machine learning with better learning techniques and capability to adapt itself to the new data, and it mainly comprises of a neural network. So we'll see in a better way how we can understand these terms. So first of all, AI, the term AI was coined by John McCarthy in 1956. And as the definition says, it refers to the theory and development of computer systems which will have the ability to perform the task requiring human intelligence, such as visual perception, speech recognition, decision making, or translation between languages. So you can see all these tasks are really intelligent dependent tasks, cognitive tasks. And if the machines are able to do that, then we can call them a artificially intelligent machine. And one example could be a self-driving car. So they can perceive the environment, they can understand what's going on in the environment, and then based on their understanding, they can take actions like whether they have to turn left or they have to turn right. So this can be considered as artificially intelligent system. Now, what is machine learning? Again, the definition is that something that some machines that can learn themselves, or improve over experiences. But just to give an example, I use this example. Suppose you are doing a math problem, and a teacher teaches you the math like 2 into 3 is 6, or 2 plus 2 plus 2 equal to 6. And when you see this, your brain automatically develops or learns an underlying pattern behind these formulas. So your brain, you may not realize it, but based on the examples, you will figure it out, why 2 cross 3 is 6, or why 2 plus 2 is 6. And next time when you sit for a test, and when a new problem is given, based on what you have learned, or that model or the pattern that you have developed, you'll be able to solve new problems. So that's what even machine learning is. They, based on the data that they see, they develop this pattern, what pattern is there in the data, and based on that pattern they can solve new problems. Now, what are the different types of learning in general? So there are, four major types of learning. I can categorize. We can usually in literature we categorize them in supervised learning, semi-supervised learning, unsupervised learning, and reinforcement learning. So let's see what those are. So first of all, let's see what supervised learning is. So as the name suggests, supervised means there is some supervision going on during the learning. So that supervision is given in form of the answer or in form of the labels. For example, I ask a machine to classify between cars and non-cars. So along with the input, which is the image, I will also give them the answer of it. So I'll it's like the teaching the kid. So you show the kid a car and you say it's a car. So it's able to relate the answer car to the question this image. And then you show another image and say it's not a car. So again you are giving the input or question as this image and answer is not a car. Now this supervision signal is not only in form of these labels, it can be in other form, like for example this translation. So if you want to translate between English and French sentence, so your English sentence could be input and you will give a corresponding French sentence as a supervisory signal. And same can be done for loan applications, or whether a user will click on a given ad or not. So you can give an input and you can give a supervisory signal, and the model will learn based on that. Then is the unsupervised learning, where you just have the input and you don't have any supervisory signal. Okay, and based on the structure or the patterns in the input, the machine has to themselves figure out what pattern is there in this data. So for example, if you see this figure, in case of supervised learning, it's clearly labeled that this is cross, this is circle. And now it becomes easier that you have to just learn a partition or a classification line that classifies this to different data. But in case of unsupervised learning, both data look similar and you cannot classify. So only you don't have any supervisory signal. So only way to do that is based on the behavior. So these circles, although both are these circles form one cluster, this another by themselves without any supervisory signal. And then is the semi-supervised learning, which is in between supervised and unsupervised, where you will give few images will have labeled, or few input data will have label, and most of them would be unlabeled. It will be just data, and based on this learning on this few sampled example, they will develop a pattern, or they will develop a learning in order to understand information from this unlabeled data. So you can take this session example of this session as semi-supervised learning. So I'm just giving you some initial cues or initial definitions, so some supervision signal. But later when you go and start learning, you will explore of your own without any supervision. So it could be taken as example of semi-supervised learning. Then the fourth kind of learning is the reinforcement learning, where so you can understand this with example of game, and here is example of Mario. So you will have a environment and we will have an agent, and this agent will observe this environment, and based on this observation it will perform some action. And then based on this action, it will something will change based on the action, and based on the action it will be rewarded. And based on this reward, it tries to learn in order to achieve better and better reward. So it's one example I could give is like, suppose a kid, it goes and touches a fire. Now it knows that burns, so it gets some negative reward, and next time it won't touch the fire. So same way, based on the reward, it will perform its action, and based on that action it will learn how to interact with the environment. And this was the one which was used in the AlphaGo. Now, majorly, you can categorize the problems in machine learning mainly in two sections: regression and classification. So let's see what it is. So one example would be the weather example. So suppose if I ask you what is the temperature tomorrow, so it will be some number like 84 degree, 90 degree, 10 degree, 20 degree. So if there is a real number, which real number to a question, that is a regression. And suppose I ask you whether it's hot or cold. So I ask you to put in some category, so that becomes the classification. If it's a real number, real value, regression. If you're putting into some class category, it's classification. So let's see some more example. So this is another example of regression. Suppose I ask you, put the bounding box or the location of the stop sign. So the location would be some real number, some coordinates, 10 cross 10 by 20, or 10 comma 30 or something. So this real number, it's a regression. Another example would be, given temperature, can you predict what will be the ounces of water consumed? Or if I ask you what amount of coolant or fluid would be required for this engine. So it will be some real number, 16 ounces, 20 ounces. So this is a regression problem. Then classification, as I said, is to put into category. So I give you this image and I ask you whether it's a normal retina or a diabetic retina. So this you're assigning to some class. This is classification. This is example of a binary classification, and we can have multi-class classification like this, where we have an input and we ask where to in which class to put in, whether it's a panda or it's a dog or it's a cat. And another example is your photo tagging. So each face is one class. Given a face, which class you'll put in, whether it's Sam or it's Harry or etc. And another example is in your mailbox, in your Gmail box, where your mails are categorized as primary, social, promotions, etc. Now, the most commonly machine learning algorithms used are linear regression, logistic regression, decision tree, SVM, gradient boosted trees, KNN, neural networks, clustering algorithms. So I won't be discussing all those. This session is just for introducing with the terminologies. But one algorithm neural network I'll touch upon, because neural network primarily constitutes the deep learning that we talk about. So what is neural network? So as you can, as the name suggests and you can see in the picture, this neural network is loosely inspired by this biological neuron. So this is a biological neuron where we have some inputs coming in the form of dendrites, and this is the cell body, and it throws out some output in terms of axons. Now the same is replicated here. We'll have some unit, so there will be some input and there will be a function that does some calculation on this input, and then it throws out some output. And this unit, this single neuron that we see here, if we connect it in different architecture, we formed it as artificial neural network. So this is one form of artificial neural network called fully connected neural network, but there are other form of neural network. So this connection from one neuron to others and arrangement in layers, this is the artificial neural network. And that's why and that's terminology deep learning, that also comes from this architecture, because if you see here, the neurons are arranged in form of layers, like input layer, layer 1, layer 2, layer 3, output layer. So if there are more number of layers, that's why that we call this term as deep learning. It gets deeper and deeper. So again, let's define the deep learning once again. So whatever learning techniques, different types of learning or task I discuss, it's valid for both deep learning and machine learning, because as we see, deep learning is a subset of machine learning. So but just let's see what deep learning is in essence. So before that, when we do any learning, basically we follow two steps. One is feature learning or feature extraction, and another is learning from those features. Now, when I say features, what do I mean by it? So this is an example from Andrew Ng's slide, from his deep learning lecture, which explain what features are. So suppose this is the input and this is the image. So its input will be in form of pixels. Now if I give you pixels, it's tough to make sense of it. So suppose I ask you, even as a human, that red color or black color or green color, it will not make any sense. But suppose if I say handles and wheels, then it makes sense to you that if it's handles and wheels, then it should be bike. So feature learning or feature representation means better way of representing the input. So instead of representing the pixels, if we can represent this bike in terms of handlebars and wheels, we can easily classify whether it's bike or not a bike. So given any input data, here I'm taking example of image data. Given any input data, always the goal is to learn a better representation of it, so that it's easier for the algorithm to learn in a better way. So in every algorithm, either we extract it, design the feature extractor, or learn it, we have to do this step of feature extraction, then learning. So now let's see what's the difference between machine learning and deep learning. So in machine learning, what was happening, this step of feature extraction was manual. So there was some domain expert who was designing algorithm based on the data in order to extract the features, and then this machine learning algorithm then this features was fed to machine learning algorithm, and the learning was being performed. Whereas in deep learning, it's end-to-end learning. There is no domain expert required to do the feature extraction. You just feed the input, the feature learning and the learning from the features take place in the algorithm itself. So that's one major difference between machine learning and deep learning. And to generalize it, in traditional machine learning, we had this feature extractor step. Here we have end-to-end learning. Now the two major highlights of deep learning, as we discussed, is end-to-end learning from input to the output without any feature extraction. And this actually helps because you don't need domain expert, and also many times domain expert, or as a human we may miss out various features which unknowingly. But deep learning, since it learns the feature from the data itself, we get better features. And another essence of deep learning is learning the features in hierarchy. So since it learns the features in hierarchy, it's getting very robust features, and the learning algorithms get really powerful. For example, here we have the input pixels, and first it will learn lower level features like edges. From these lower level features, it will learn better abstract features or higher features like these noses, object parts, lips, nose, eyes. And from these parts, then it constitute your face, and thus the face recognition. So this hierarchy of features helps to learn better features and perform the task in a better way. So that is deep learning. And what is this term transfer learning? This also is a term which you'd be, you may encounter. So suppose you know how to, ride a bicycle, and then you go and ride a motorbike. Then it's not like it will be something new for you. The learning that you have developed here, you can transfer it to here, like learning the bike. So same refers even in the machine learning domain. And this was also predicted again from end-to-end slide that transfer learning would be leading to commercial success, and that's what has happened. And now unsupervised learning and all is taking up self-supervised learning and all. But transfer learning has really helped for many applications. And why this happens, for example, here suppose this is one problem where you have to learn faces, and this is another problem where you have to learn cars. Now since deep learning learns features in hierarchy, the basic features like edges or some parts, it remains same in many of the different tasks or many of the objects. Like there will be lines in faces, and there will also be lines in cars, and there will be lines in elephants and even in chairs. So this knowledge which was developed in learning faces, this knowledge can be transferred on learning cars. And the knowledge which was learned in faces can also be transferred to other tasks. So this kind of transfer learning helps to learn in different scenarios when you have less data, and instead of starting from scratch, you already have some elevation that you get by using previous knowledge. So that you can just relate it to how human learns, and it's basically that thing. And now, once I've touched upon all the terms, how this learning pipeline takes place from end to end. So there are five major steps, uh, broader steps. So starting from data acquisition to data cleaning, and then data preparation, then feature engineering, then model training and evaluation, and model deployment. So let's see them step by step. So first is data acquisition. So given a problem at hand, you have to acquire data for that problem. Now the data could be in any form. So here are some examples. So this data could be in form of signals, 1D or 2D signals, like this signal waveform coming from this mic, or it could be in form of images from the camera, and it could be different kind of camera, IR camera or X-ray camera, or normal visible camera, or this point cloud coming from the lidar, or different sensory time series signals coming from various sensors, or it could be the NLP domain, like the text data. It could be any data depending on the problem at hand. Now, once you have acquired this data, next step is to clean this data and prepare the data in a form that can be used. So raw data is directly not usable, so you have to prepare it. So for example, there could be a problem of missing data. So you record various sensors, but due to some glitch, some sensor did not have any recordings, or they had some faulty recordings. So you have to, eliminate all this, or you have to, kind of fill in all this missing data based on your domain expertise or based on the behavior of the signal, and you have to prepare the final you know the final good signal that can be used. Another example could be data representation. So the data input data that you get will not be in a form that you can use directly. For example, in the NLP you will have this text, but we cannot use text, so these words need to be represented by different vectors or different numbers like this here, so that they can be used. Or another example could be doing some kind of pre-processing. For example, in the image data, this is very dark, so you have to kind of clean it, make it brighten so that it is understandable. And also suppose this kind of defect is very small, so you have to enlarge it. And then could be data preparation based on the learning. So suppose I'm using a supervised learning, so I have to assign supervisory signal or labels to this data. So I have given this input image, what is it? So it's a horse. What is it? It's a zebra. So you have to assign this kind of signals and prepare your data. So once you have data acquisition, you do this data preparation cleaning to have this final prepared data. And another step that you can perform is feature engineering. So depending again at the task which you have at your hand. So another one example of feature engineering could be this representation of the words in embedding. So you have these words represented in vectors, but it doesn't mean anything. So you can represent them in some better vectors. Like this is a word to vector, where the different words would lie in similar space, in similar high dimensional vector space. So for example, men and women are similar in nature, so they will lie similar to each other. And example, this at some attributes like long, longer, longest, they should be lying at one place. So from low level to higher level features, the same example that I gave, from pixels to representing the bike in form of handles and wheels. And this could be done in image also, from raw input to some better features like edges or some shapes or object parts. And there could be scenarios where you have to design new features depending on the problem. So for example, you have the location of the human and location of the pedestrian, and you want to know if the car will hit the pedestrian or not. So you could come up with new feature, for example, as distance. What is the distance between these? And you can feed this distance feature for the algorithm to learn when the car may hit the pedestrian. So now once you have done your data acquisition, data pre-processing, cleaning, preparation, and you have obtained good features, now comes the main part of model training. So there are so many algorithms. So depending on the problem of hand, you can choose which algorithm to use. And this training algorithm, is iterative process. So you'll feed the data to your model, and then you will see its performance, whether it's doing good or not. And then based on the performance, you may need to tweak various parameters of the model, or even some cases, you may have to change the model entirely, use a different model based on what evaluation you see. And now once the model has been trained, so you will have a separate set of data called test set. You will see how your model is performing on the test set, which it does not see. So after this training, evaluation, and testing on test set, you get the final best trained model for the problem at hand. Now what you do with this trained model? Now you have to deploy it somewhere so that you can use it. So this is your trained model. So either you can package it some kind of web service API and all, and then once you have packaged it, you can deploy it in some physical hardware, like some boards that you can easily integrate to any of your product, like FPGA, ASICs, Raspberry Pi. Or you can rent some cloud services like AWS, Azure, or Google Cloud. You can host your model there. And once you have hosted your model on some hardware or cloud, so you will receive a new input signal from the environment, and based on what your model has learned, it will give you output based on what input it sees, and this is called as model inference. So this is the entire pipeline of from data acquisition, cleaning, learning, and deployment. Now that's all from here. So let's quickly revise. So what we saw, that AI is nothing but a new programming paradigm. We saw some current AI trends. We saw why this AI hype. So all of a sudden, in this decade, that's because of deep learning. And then we saw, four reasons of why deep learning, started working well. Then we saw definition of AI, ML, and DL. And then we saw that ML refers to nothing but being explicitly like learning without being explicitly programmed. And then we saw supervised, semi-supervised, unsupervised, and reinforcement learning. Then we saw two major kinds of task or problem, like whether you have to predict some real number, or you have to put your data in some categories. And then we saw what deep learning is. It's a neural network, but it provides end-to-end learning, and it learns in hierarchy. It learns features in hierarchy. And then we saw the ML pipeline from data acquisition, data engineering, model training, and model deployment. So that's it. And again, I'll not discuss the image based use cases. Again, if